Hi everyone. In this video, we will discuss curl, a geometric quantity related to vector fields that helps us understand how vector fields rotate, along with Stokes's theorem, the first of three theorems in which we will see an analog to the fundamental theorem of calculus for higher dimensional integrals. So we first want to begin by simply defining the curl of a vector field. So imagine we have a vector field F, and we'll express F in terms of its components, and we'll call the X component P of XYZ, the Y component Q of XYZ, and the Z component R of XYZ. And let this be a differentiable vector field. Then we define the curl of F as the vector field. So the curl is a quantity related to this vector field F, but itself is another vector field. So the curl of F is the vector field defined by the following equation. So it's the vector field whose X component is the partial derivative of R with respect to Y minus the partial derivative of Q with respect to Z. Its Y component is the partial derivative of P with respect to Z minus the partial derivative of R with respect to X. And its Z component is the partial derivative of Q with respect to X minus the partial derivative of P with respect to Y. Now, this is one way of defining the curl. As you can just see from this expression, like this would be really hard to just like remember off the top of your head, right? I don't think of this, like when you ask me what the curl is, this is not what I would immediately say. Like I wouldn't say, oh, this is how you calculate the curl of a vector field, although it is equivalent. So the first thing we want to explore is sort of how on earth to actually remember how to calculate this. And again, this is all stuff you may have seen in a Calc 3 course, but we want to sort of quickly review. The curl of F is more conveniently remembered as this sort of 3 by 3 determinant. Okay, so one way to think of it is to think of this as the determinant of the first row are the vectors I, j, and k. The standard basis vectors I, j, and k. The second row here, these are all operators, right? So I think of this as take a partial derivative with respect to x, take a partial derivative with respect to y, and take a partial derivative with respect to z. And then the third row are just the components of my vector field p, q, and r. Okay, so it's pretty easy to see, right? If I do an expansion by minors here, right, I will get that. Okay, if I go along the first row, so I have I here times the submatrix here. Okay, so I would get d dy q and d dz r times I. Then I would get a minus, right? So going to the second entry, so this is going to be j, and I'll get a d dx p and a d dz r j. Okay. And then the last component, so again, that'll be a plus now, k, and I'll be left with this submatrix. And so I'll have a plus d dx p d dy q k. All right. And now for each of these, right, if I think of this. Now, this is where, again, it's sort of, this is a nice way of thinking about it, but it's not really a determinant, right? Normally, when we think about a determinant, right, I would say this times this, right? So for the submatrix, I'd say take d dy times r. Well, this is like an operator, and this is a function. That times doesn't really make sense. We really want to think of this multiplication as being apply the operator to the function. So I want to take a partial derivative with respect to y of r. That'll give me dr dy. Oops. And then minus this product, but again, not really a product. This would give me dq dz I. And now here, I've got a minus, so I would have a minus dr dx minus dp dz. But one of the things I noticed is I could move this minus inside and just switch the order of these. So I'm actually going to make this a plus and then just switch the order of these. So I'll have a dp dz minus dr dx j plus, now here finally I get dq dx minus dp dy k. Okay. And again, what I see here, right, is that this is exactly how I defined the curl on the previous slide. So if I just jump back here for a second, and I'm sort of overlaying here, but right, I can see that some of these components are giving me back the same thing. Oops. All right. So this really is, this really is giving me a nice way to remember how I compute the curl. Okay. Now, one sort of shorthand that we often use then, right, if I look at this determinant notation, right, this really looks like a cross product, right? It looks like a cross product of this ddx, ddy, ddz with p, q, and r, okay? So one of the things we often do is we define this operator, which we often refer to as del, okay? So this upside down nabla is backslash nabla in tech, but this this really isn't really a vector because the x component here is an operator, the y component is an operator, the z component is an operator. So this is an operator. When we say it's a formal vector, we're really saying it's not really a vector. We're just sort of going to formally think about organizing it as a vector. And if we do it in that way, then we can think of the curl as this del operator cross the vector field f, right? Because this is just the vector whose components are the functions p, q, and r, right? So again, this del cross f would give you exactly this determinant form back, right? All right. So this is how we often, think of these things. It's really convenient, if you wanted to calculate, just as an example, you wanted to take the vector field, which is, say, this is one we looked at in a previous video, xi plus yj plus zk, right? So if you just wanted to compute the curl of that, then a really straightforward way to do that, right, is just to say, okay, this is ijk ddx ddy ddz, and then just xyz. And now, if I start writing this out, right, okay, again, I can just do the expansion by minors here. So it's I times this subdeterminant, so that would be d dy applied to z. What's the partial derivative with respect to y of z? Well, z is constant as far as y is concerned. That's just 0. Minus d dz applied to y, again, is just 0. Okay, so there's my I component. Minus my j component. So again, marking out this row and column, I get d dx applied to z, that's 0, minus d dz applied to x, which is 0. Now for my kth component, I'm back to a plus again. So d dx of y is 0, minus d dy of x is 0. Okay, and so in fact, I get that the curl of this vector field is the 0 vector. So again, now notice, right, I want to emphasize the curl of a vector field gives you back another vector field, right? So this is not, it's not here that the curl is the single vector 0. At every point at which this vector field is defined, which is on all of R3, so at every point on which this vector field is, defined, the curl gives you back the vector 0. So the curl is 0, the 0 vector at every point in R3. Now, of course, if we go in here and change some of these things around, so let's say I was to change this, let's say I was to swap X and Y, but then I'm actually going to replace that Y um, with, or replace that X with an X squared, okay? So if I come down here, I can sort of, see quickly what changes. And I'm just going to have a Y and an X squared, okay? So you'll notice that actually this first component is still going to be 0 minus 0. Partial derivative with respect to y of z, partial derivative with respect to z of x squared. The second component, same thing, because you're going to get d dx z, d dz y. Okay. But in the last component now, okay, you're going to get d dx of x squared. So you're going to get a 2x. So d dx of x squared minus d dy of y, which is just 1. And so here your curl is 2x minus 1 times k. So what is this telling you? This is telling you that at each point where this is defined, this curl is a vector that points straight up in the z direction, or straight up or down in the z direction, and its magnitude depends on what x value you're at, right? So again, this is giving you back I want to emphasize that the curl of a vector field is another vector field, right? And we just, in the first example we just got that it was constant, the constant zero vector. In this case, we get that it's not constant. All right. So again, the curl, this is something you've likely seen before, you've calculated before in a Calc 3 course. And if you want some more examples of calculating these things, both the Apostle textbook does have some worked examples, but any Calc 3 book online will have plenty of examples. Okay, that's if you want to go back and just remind yourself how to do some more of these calculations. All right, but then that's sort of funny. My face was immediately in the middle of that. So now the question becomes, okay, great, I can calculate this, but what does it mean, right? So one way to think about the curl is you sort of want to imagine that you are placing this little paddle wheel in your vector field. So imagine I have a vector field, just say on the board here, right? And I drop this little paddle wheel in here, and I'm going to let the paddle be moved by sort of the vector arrows. So I can imagine those vector arrows are like water flow, right? Or some sort of fluid flow. So I drop this in here, and I look at sort of instantaneously what happens to the paddle wheel. Now, of course, in real life, if I drop it in there, it may start moving, right, left to right, up or down, but I really want to focus in on instantaneously sort of what is the rotation, right? So one of the things that curl is capturing is the rotation of the vector field, okay? So the curl vector that you're going to get back at this point is really going to tell you two things. The direction of the vector is going to tell you sort of the axis of rotation. Okay, so in this example that you're looking at here, right? It's rotating this way, and so what you do is you put your right hand in the direction of the curl, or sorry, of the direction of the vector field is turning. So in this case, the paddle wheel is turning this way. So I put my hands in this way, and then I look at you have to use your right hand. Then you look at, okay, if I turn my fingers in this direction, which way is my thumb pointing, right? So in this case, it's pointing away from, what am I trying to say? It's pointing away from the board, like it's pointing back towards me, right? So that's giving you sort of the axis of rotation, okay? The second thing that it's giving you, right, so it's a vector, so its direction is telling you the axis of rotation. The magnitude of that is sort of telling you something about the speed of the rotation, right? It's sort of the angular speed at which this is rotating, right? So if the vector is very large in magnitude, it's rotating very quickly. If the vector is small in magnitude, it's not rotating very much at all. If the vector is 0, like that first example we saw, then it's not rotating at all. We call those vector fields irrotational. And so that's another property that vector fields can have. Another way to think about the curl, and actually this is actually another way you can define the curl. We defined it formally sort of in terms of coordinates, but another way that you can think of the curl is you can think of the curl of a vector field as taking the limit, say, as, let me write this down first. So imagine, and sorry, I should actually, let's see, this should be. So the idea here is, especially in 3 dimensions, this sort of works in 2 dimensions. This is a little harder in 3 dimensions. In 3 dimensions, you can think of, so take your point and enclose this point in some volume. Okay, so you enclose this in some sort of region, something here. Okay, and the question you want to ask yourself, so for any volume you fit around here, you could compute. So this is 1 over the volume of this region V, okay, times the surface integral of f ds. Okay, so you basically look at how this is, how things are this flux integral is telling you, how things are sort of flowing over this. Okay. And what you ask yourself is, what happens as I sort of collapse this volume down to 0? So as I take smaller and smaller and smaller regions. Okay. Now, again, this is another way of defining it. To show that this is equivalent to the other definition is fairly technical. And so we're not going to get into that. But this is actually another really helpful way of thinking about it. And in fact, this gives rise to the notion of curl being what we call a circulation density. So this quantity is telling you sort of how this is circulating over this, and this is dividing that through by the surface area, essentially, right? So it's giving you sort of a per unit surface area measurement there. Yeah. So this is just another nice way to think about curl, and it'll be another helpful way in a bit as we try to make sense of some theorems related to curl. So again, curl is something we can calculate. It tells us something, either if we want to think about it as the rotation of the vector field or this circulation density concept. And from sort of just a mathematical perspective, it's a type of derivative of a vector field. In fact, if you go on and study other areas of math, right, you can formalize things called exterior derivatives and understand these in broader context. But for now, it suffices just to say that, right, this curl is some sort of derivative of a vector field. Okay. All right. So we want to think about then, if we have this derivative, the curl of f, if I integrate it, the fundamental theorem of calculus, right, I should be able to sort of say something about that, it feels like, right? Or at least my ability to say that would be sort of nice, because there would be something like a higher dimensional fundamental theorem of calculus. So what if I had some surface S and I wanted to integrate the curl of the vector field over that surface S? Okay, so let me start. Let me imagine my surface S here is just this flat rectangle. Okay, and if I came over here, okay, I could think about trying to measure let me think about sort of measuring the curl at sort of the center point of each of these here. Now, I've drawn this with 12 squares. You sort of want to imagine that there are many, many squares and they're all sort of infinitesimally small, but let's just draw a picture with 12 squares. Now, if I assume that my vector field is continuous, okay, and these are all really, really small. So I could say, for example, that maybe my curl shouldn't be able to change sign, right, going, between any 2 rectangles. Now, in practice, right, it could go from big to smaller to smaller to smaller to 0 to negative to negative to negative. But if it's continuous and we're sort of zoomed in on one piece, right, if we zoom in far enough, then all the curls should either be positive or negative. So let's say, that would mean that all of these are sort of rotating in the same direction, right? So the curl has the same sign, or sorry, has the same direction, right? The curl is a vector quantity. Okay. So if I do that, sort of each of these, right, around each of these points, I'm going to have, things pointing in the same direction. And let me even add some more arrows to some of these to help us see what's going on here. Okay. And let me maybe do one more, or let me do a couple more here just to help illustrate what's going on here. Okay. And again, these are all rotating in the same direction. Whoops. Keep wanting to draw this one in the wrong direction, apparently. All right. Now imagine if we think of that curl as the circulation density, okay? If I sort of think about what's going to happen along this edge, right? So along this edge over here, right, as I add up what's going on here, that's going to be the same as what's happening here, but I'm traversing these curves in the opposite direction. So I'm going to get sort of, some positive here, but a corresponding negative entry here, which means along this edge, I'm going to get cancellation, and that's going to add up to 0. And the same thing's going to happen along all of these edges, right? Along all of these edges, I'm going to get sort of some piece in one direction and a piece in in the opposite direction, right? Which is going to give me cancellation in the curl. Okay. So along all of these, and again, I'm not going to draw them all out, but along all of these anterior edges, right, things are going to add up. I guess I will draw them all out to 0. Okay. But what happens not along the interior edge? Well, along the exterior, along the boundary of this surface, which I'm going to call C, I'm going to get some non-zero amount, right? And so the question becomes, what is this non-zero amount? Well, I can simply keep track of, right, along each of these exterior edges, right, what is that, right? I'm going to pick up non-zero quantities along all of these edges, right? Right? And so what's going to happen is that all this stuff on the interior is going to cancel out. And what I'm going to be left with at the end of the day is just the integral over that boundary curve C of f d alpha. I'm going to end up with this line integral. Everything on the interior is going to cancel out. I'm just going to be left with the value on the boundary. Okay, so sort of the overall strategy when we think about how we're going to integrate this is we say, well, take your surface and divide it into a bunch of small pieces, right? Call them delta S1 up to delta Sn. And again, because we're thinking about a surface in 3 dimensions, if you sort of zoom in far enough, if you make all of those little pieces, small enough, then they'll sort of locally appear flat, right? And then on each small piece, we can apply what we're later going to call Green's theorem, right? But actually, for the time being, I can think about just this argument here, right? I'm going to apply that to get that the curl on any of those little flat surfaces, right? The integral of the curl over the surface ought to be roughly just the integral over the boundary of that piece of f dot d alpha. And then if I add all those pieces up and take an appropriate limit, that gives me back what we will call Stokes' theorem. Okay, so let's see then, we're sort of previewing, okay, what would happen if we did this? Oh, we'll get this thing that we want to call Stokes' theorem. So now let's say what Stokes' theorem actually is. Just to have this here and to quickly summarize first though, right, the whole idea is we do this on each little of those little rectangles. The interior edges all cancel out. And the outer boundary is the only thing that survives in the sum. And really the reason for putting this up here is that I want to emphasize that this is exactly the same sort of thing that happens when you prove the fundamental theorem of calculus for functions of a single variable. So for example, if you go back and look at our proof of the fundamental theorem of calculus from Math 5610, you'll see that we have this sort of telescoping sum where a bunch of interior terms all cancel out, and the only thing you're left with are the values on the boundary, right? Well, here the same thing is happening. It's just that the values on the boundary now, because we're in higher dimensions, is this curve living in R3, right? So we actually have to do a line integral here, right? Instead of just evaluating the function at the endpoints. But what we're doing is we're essentially just adding up all those values over the boundary, okay? So again, this is very similar in spirit to the fundamental theorem of calculus, where we have an integral of some sort of derivative thing over a whole surface, and we're going to show that this is equal to just looking at the function along the boundary. It's just here that when we say looking at the function along the boundary, we actually have to integrate over the boundary, whereas in the regular fundamental theorem of calculus, we just evaluated at endpoints and took a difference. All right, so now here's our formal statement of Stokes' theorem. And I'm actually going to just step out of the frame here in just a second. It's a very big theorem. I had to use the whole screen to get it up here. So I'll step out of the frame, but we'll talk through this. So let S, S is going to be a smooth, simple parametric surface. It's going to be parameterized by R of t, where t is some region in the UV plane bounded by a piecewise smooth Jordan curve. Now, I'll tell you in just a second what Jordan means, but it's piecewise smooth Jordan curve, which we'll call gamma. And let the parameterization R be one-to-one with each of the components of R having continuous second-order partial derivatives on an open set which contains T union with gamma. Let C denote the image of gamma under R, and let P, Q, and R be continuously differentiable scalar fields on S. Okay. Then, if we do that, then the surface integral of the curl of F is equal to the line integral of F over the boundary curve C, where n is the unit normal consistent with the orientation of C. And there we mean consistent in terms of the right-hand rule. So you want your unit normal to be the one that when you follow that orientation of C, you get the unit normal that's pointing in the right direction. Okay. So now that we've got this theorem up here, let me draw a picture, okay, to help just understand. So we start over here in parameter space, right? This is sort of UV space, and we have some region T. Now, we also have the boundary of T, okay, which is this piecewise smooth, it needs to be a piecewise smooth Jordan curve. Okay, so what do we mean by a Jordan curve? Okay. My red marker is fading here and getting very squeaky. Okay. So by a Jordan curve, I just mean that it is simple. Simple meaning it doesn't self-intersect. And closed. Okay. So for example, this is not a Jordan curve because it self-intersects. So this is not simple. We having trouble writing the word simple today. Yeah. This curve is simple. Oh, sorry, this is not simple, but it is closed. Okay. This is simple, but not closed. What we want is simple and closed. Something like this. This is simple and closed. This is a Jordan curve. Now, you can spend a lot of time talking about Jordan curves. The fundamental thing about Jordan curves is Jordan curves are curves that if you have a Jordan curve in the plane, it separates the plane nicely into basically an inside region and an outside region. Any other curves, you run into issues, right? Certainly if they're not closed, like what would inside and outside mean. You also run into some issues if your curve is not simple. So we sort of want to just avoid that. Because again, like what happens at this point, there are issues there if you take a non-simple curve. So we want this nice Jordan curve. That's basically going to give us a nice region and enclose a nice region in the plane. All right. So we sort of have this set up in parameter space. And then the question becomes, okay, now we map that to our surface. What does that give us on our surface? Right? Okay, so now our parameterization R, oops, getting up into the text here. So now my parameterization R is going to take me over here into R3 to my surface. Okay. And right, it does whatever it does. Okay, so here's my surface S, which is just R of T. Okay, and here C is the image of gamma under R. Now, it's sort of important to note that we need to be cognizant of the fact we have this condition that R is 1-to-1. So you might feel like naturally, if I just pick this up and bring this over here, right? So the natural way to take it, I'd take it and lay it down here, and gamma would map nicely to the boundary here of this surface. That is only true if R is 1-to-1. Okay, so thankfully we have that assumption, right? So I know over here, I'm going to end up with this boundary curve C, which is just going to be R of gamma. So that's what all of these things, it seems like there's a lot of defining going in here. There sort of is, but it's really not that complicated. You have T and the surface, which is S, but that's really just what R does to T. And then you have gamma, which is the boundary of T, and that maps over here to the boundary of S. Okay. And so again, all this is saying is if I want to take and add up the curl at each point in here, okay, then that's the same as just integrating the vector field along this curve C. Now, again, that curve C is in 3 dimensions, right? So, you know, it's maybe still not a trivial calculation, right? But this is helpful. Now, if you ever go on and teach a Calc 3 course, you know, this is often something that's sort of stuck at the very end. And often the sort of examples that you see are really things that are just constructed to apply Stokes' theorem to. Okay, I actually think that Stokes' theorem, what gets lost a lot is some of this conceptual stuff we've been talking about, right? What is curl actually measuring? Why is Stokes' theorem, you know, why is it actually true? And again, it just gets turned into, oh, here's another way to calculate things. But again, its greatest power really is in an analytical sense that it allows you to reduce this integral over a surface to an integral over a lower dimensional object, to just an integral over the boundary, right? So we're really able to calculate this thing that requires sort of 2 dimensions worth of values by only looking at a 1-dimensional subsets values and integrating over that, right? So in the same way that you know, the fundamental theorem of calculus is so valuable just in terms of reducing this integral over an interval to information about an antiderivative at 2 points, this is doing the same thing, okay? Now, computationally, you can run into some of the exact same problems. And in the next video, we will look at sort of extensions of this. So we'll see how some of this works, but you run into the same issues of the hard part then becomes finding antiderivatives. So if you have the double integral over a surface, how can you tell whether or not this vector field you have here might be the curl of some other vector field, right? That's a non-trivial thing to do. It involves maybe solving some sort of weird system of partial differential equations, right? So that could be quite difficult. But again, theoretically, you don't have to sort of worry about that. Theoretically, you go, oh, okay, I'm integrating this thing here. Just call it the curl of f. Here's how this all works out. Okay, so we're going to stop this video here. The whole point here was to introduce the notion of curl and the idea of Stokes' theorem and what it's all about. In the next video, we'll talk a little bit about how you would prove Stokes' theorem. We'll talk about a special case of it called Green's theorem, and then we'll sort of look at in practice how this gets used.